And so what we want to do very often is not have things on a mole basis. That's nice when we are doing chemical reactions, but very often in engineering we need things on a mass basis. And so let's now look at the air-fuel ratio on a mass basis. RAF is equal to the mass of air over the mass of fuel. And in this case, we'll be using the molecular weight of the substances to correct. These are moles, so let's look at that. So we have 11.9 moles, and the molecular weight of air is 28.97 kilograms per kilogram mole. We're dividing by 1 mole of fuel times the molecular weight of methane, which is 1604. So on a mass basis, this is 21.5 kilograms of air per kilogram of fuel. And so we're interested in that, and so very often we'll find this. And what we can do as well is that we're interested in the fuel-air. This is the air-fuel ratio. Sometimes we want to know the fuel that we're using. So RFA is equal to 1 over RAF. So in this case, it's 1 over that 21. So it's 0.0465 kilograms of fuel per kilogram of air. So when we're balancing first law equations with reactions, very often we'll do this. And we'll get to first law in a little bit, but that's ahead. Some exciting things to look forward to. And now let's look at the molal analysis of the products of combustion. And so what we're interested in is first we're going to find the total number of moles, and then we'll find the moles, the partial, not the partial pressure, but the YI, the mole fraction associated with each one. So if I look at the total, I have 1 plus 2 plus 9.4 plus 0.5 is equal to 12.9. So that's the total number of moles that we have. So for CO2, I have 1 divided by 12.9. So this is equal to 0.0775. For water, we have 2 divided by 12.9, and that's equal to 0.155. For N2, we have 9.4 divided by 12.9. So this is equal to 0.729. And for O2, it's 0.5 divided by 12.9, and that's equal to 0.0385. So this gives us what the molal analysis of the products are. And it's like, why do I care about that? So part of why we care about that has to do with the dew point of the products. So we're interested very often in operations in making sure that we don't have things below the dew point. So if P total is equal to 101.3 kPa, then pH2O is equal to YH2O times P total is equal to 0.155 times 101.3. So this is equal to 15.7 kPa, and Tsat corresponding to this is about 54 degrees Celsius. So what happens when I have this reaction, if the temperature falls below this, you'll get water coming out. You'll get liquid water. Now you see this when you start up your car in the morning and it's cool out, your water comes out the tailpipe. Why is that? It's because the temperature of the products, because everything is cold, is below the dew point, and then there's condensation. Once everything heats up, then there's no condensation. You don't see it. It's vaporless. What I wanted to do next is look at the combustion of coal. It's example 12.3, and I wanted to go through that just to understand it and to provide a little more information than is in the textbook, and to reinforce if we're burning a solid like coal that has ash in it, wood has ash in it, garbage has ash in it, vegetation has ash in it, so not all of those substances are combustible. We need to see how to do that, and since this is an important area in terms of power generation and people are looking for using renewable resources like wood, but they all have challenges associated with them. So now, again, this is example 12.3. And with this, we're given coal, and we're given it on a mass basis. And so we have coal. And in fact, you may want to look at the problem and how it's written. So now we have it 74% carbon, 5% hydrogen, 6% O2, 1% sulfur, 1.2% N2, 3.8% water, 9% ash. So all these things can be oxidized except the ash. So now what we have to do is to take this and find the Xi on an ashless basis. So we want Xi ashless. So if I take this, if I divide this, I'm looking at finding what this is. So if I do 0.74 divided by 0.91. So this is the ashless basis. I got rid of that. So this is 0.813. So with it, now I'm going to do the same calculation, but I'm not going to, I'll write these all out, but I'm not going to do it here. 0.055. So this is right in the text. 0.066. 0.011. 0.015. 0.042. And the ash isn't there. So these are the Xi ashless. And now what we need to do is to convert that to Yi. So if I want to have a combustion equation, the analysis is done on a mass basis, so I have this Xi stuff. Now I've got to get it to Yi so I can balance the combustion equation. And part of why I'm doing this example is that this step isn't as clear in the text as I would like, so I wanted to show you what it is. So now if we have carbon, and I'm going to have Xi, Mi, Ni, which is equal to Xi over Mi. And I'm going to have eventually Yi, which is Ni over the sum of the Ni. So this information along the top, you're given some of this, but not all of it, and where it comes from. So this is the process that goes through. So I'll write this down and we'll see how it goes. So 0.813, this is 12, this is 0.0627, and this is 0.674. So, and we're going to get to where the sum of the Ni is. So this is the Ni, and now I'm going to write out all these things that are in the table, but I didn't see how to speed the process up. You know, the sound of chalk is very interesting. And so then to getting to the end, and if I add these up, this gives me the sum of the Ni, which is equal to 0.1004. So the text didn't really show, this text showed all the numbers, but it didn't show the process. So I wanted you to see the process, particularly to get the yi that we need for the combustion equation.